So, good afternoon and welcome to the last of the end-to-end exchange sessions. And we are moving now into neural network cultures. I'm not going to say anything more about it because we're in the able hands of the moderator, Matteo Pasquinelli, who's a professor in media philosophy at the University of Arts and Design in Karlsruhe, where he's coordinating this research group on artificial intelligence and media philosophy, also known as KIM. And together with KIM and the HFG, Transmedial is part of, or has been part of, a research consortium with a large number of partners, which has the support of the Volkswagen Stiftung's program on AI and the society of the future. Matteo has recently edited Alice of Your Mind, Augmented Intelligence and Its Traumas, among many other publications and books and articles of his own. His research focuses on the intersection of cognitive sciences, digital economy, and machine intelligence. And he's preparing a book, a monograph for Verso, called, or provisionally titled, The Eye of the Master, Capital as Computation and Cognition. So please welcome Matteo and the speakers of Neural Network Cultures.
Hello, everyone. I hope we have the first slides. Yes, thank you. Okay, yeah. I'd like to thank once again Transmedial and Christopher for continuing this collaboration with the University of Art and Design Karlsruhe and our research group, KIM. The event of tonight is also part of a project funded by the Volkswagen Foundation that hopefully will evolve next year in a larger research network on critical AI. Our project aims at answering a difficult but important question. How does artificial intelligence see the world? And correspondingly, how do humans see the world through the lens, through the mediation and aberrations of artificial intelligence? This question has been also part of an extremely intense Transmediale workshop on adversarial attacks in deep learning, where we discuss the vulnerabilities and political limits of machine learning, and we try to navigate the latent spaces of neural networks. A century after Cassira, we should ask, what is the cultural form, the symbolic form that is specific to artificial intelligence, to machine learning? There is a growing criticism of AI that discusses, for instance, the role of training data and the bias they accumulate and amplify. In our project, we would like to switch the focus of attention, for once, on another element, something that is found at the inner core of machine learning. Usually we say that at the core of machine learning there are algorithms, but which kind of algorithms? An algorithm is only the name of a process. What do algorithms really do? What is their result, their product? We can say that algorithms analyze data and they build a model of this data. They build a statistical model of data, a statistical model of the world. The statistical model is a complex mathematical construct. Computer scientists just call it the model. Mathematicians sometimes call it in a different way, like statistical distribution. Sometimes it takes the shape of a manifold. Sometimes it's a vector space, a hyperdimensional space. But don't worry, because even computer scientists don't have a common terminology for this domain inside the machine. But I hope we don't use too difficult names tonight. We try to bring example. But indeed, where are we tonight inside the black box of machine learning? With Vladan Joler, that is sitting with us in the audience tonight, hi Vladan, we are sketching as part of this project that wants to build a pedagogical and cultural interface to machine learning. We are sketching this new fantastic map that wants to describe the machine learning apparatus following the information flow step by step inside the machine and outside the machine. But also following this information flow and highlighting the errors, the faults, the bias, the approximation, the fallacies that we find inside machine learning. Here we represent this apparatus of machine learning as we're using the metaphor of optical media, an old metaphor that was actually suggested, introduced for the first time by Leibniz to describe the calculus ratiocinator. And we fashioned the statistical models of machine learning as optical lenses to stress the aberration and distortion of information they engender. Through AI, because it is through AI, we often perceive the world in a distorted way. And a bit ironically, we call this map the no-scope. I mentioned this because it will be launched officially next month, but it's being used during the workshop. And actually, in the spirit of the workshop, we printed many copies of this map that you're invited to pick up, and maybe also to comment and add this. They're like red markers, so this is an open project to somehow construct a collective mapping of machine learning. But let's zoom again to the point of discussion tonight. I want now to bring an example of a statistical model that is featured at this festival. I know statistical model is not a very appealing term. You cannot do many art exhibitions around them. But somehow they run in the background of our art project, our research, our society, our smartphone. This is the CSEM model, or Community Earth System Model. This is the model running in the background of the installation Azanda by Tega Brain, Julian Oliver, and Ben Ziolen at AKV. This is one of the many models we use to predict the climate today. When Greta Thunberg says, listen to science, what she really means, being a good student of mathematics, not like you probably, listen to the statistical models of climate science. No statistical model, no climate science. But these models are historical artifacts. CECM, for instance, is 20 years old and maintained in a specific institution of the world. It's in Boulder, Colorado, United States. I like the idea behind the Zander installation. It is an attempt, a very good example, of how we can make visible the invisible statistical model through which we analyze and perceive the world, in this case, climate change. Mathematical models have been always dictating politics. With machine learning, interestingly, this role of modeling of the world gets automated. Like it or not, it's time to address the impact of these statistical models on culture, society, and the perception of the environment, and to question also their vulnerabilities. And tonight, we will do this thanks to 4 fantastic contributions by science historian Stephanie Dick, data scientist Katharine Jarmul, AI scholar Fabian Offert, and engineering artist Tega Brain. Now, I should read in the most as friendly as possible the biographies. I'm happy to have in Berlin, finally, to have met Stephanie Dick. She is assistant professor of history and sociology of science at the University of Pennsylvania, holding a PhD in history of science from Harvard. She is a historian of mathematics and artificial intelligence. Her first book project, Making Up Minds, tracks early efforts to automate mathematical proof. Her second book project explored the early introduction of computing to domestic policing in the United States, including automated identification tools. So please help me to welcome on stage Stephanie, and we start this discussion on the history and the impact of models in computation and society. Do you know what is your slide? It's not a keynote. It's this one.
Thank you so much, Matteo. It's really such a pleasure to be here. Berlin is one of my favorite cities, and this is a really special event that's quite new to me, and I'm really excited to be able to share some historical perspective on these questions with you all. So actually, for most of its history, maybe some of you are aware of this, the word computer actually referred to a person and not a machine. Computers were most often women, people of color, who executed large numbers of arithmetic operations that collectively, when taken together, could solve really complicated mathematical problems that might otherwise be untenable. Human computing emerged in the 19th century when a French mathematician by the name of Gaspard de Prony applied Adam Smith's principle of the division of labor to the mental work as it had earlier been applied to physical work in factory automation. Human computers were the people who staffed the so-called factories of the mind. It should come maybe as no surprise then that people were once the measure of the machines. Machine computers were first created to do the work that human computers had done before them and to do it by the same means. When modern digital computers were first developed and their limitations and possibilities were relatively unknown, their possibilities were sounded out in terms of what people could do. What human abilities could computers be made to reproduce? How much like a human could we get the computer to be? Oops, sorry. And early artificial intelligence was born out of the belief that not only could computers replace the humans doing computer calculations, but that actually they would be able to do any of the things that human minds do. Early artificial intelligence practitioners wanted to reproduce human capacities in the machine. And drawing from a long tradition of logic and philosophy, they believed that we are fundamentally rule-bound as knowers, that our minds follow a set of rules that can be articulated, formalized, and automated. And they wanted to reproduce their own intelligence as they understood it in the machine, getting it to do what they did. AI, therefore, for them, began with introspection, with interviews. It started with people. They were trying to figure out how master chess players think, how doctors diagnose illnesses, how mathematicians solve problems and prove theorems. They wanted to map what human intelligence consisted in and translate it into automatable sets of rules. So early artificial intelligence researchers tried to identify whatever the rules are that they believed govern our reasoning, and then get the computer to proceed in the same way. But of course, computers are actually nothing like us, especially in the 1940s, and to be completely honest, no matter how well I understand and how thoroughly I study the historical reasons for it, I still actually can't imagine looking at a machine like ENIAC and thinking, you know, that thing is just like us. In fact, early artificial intelligence practitioners were more eager and willing to attribute intelligence and knowledge and the capacity for reason to these machines than many people throughout history have been to attribute those faculties to other human beings. Projects of colonialism and enslavement and hierarchies of gender and race have historically denied those higher human faculties to the people they colonized and enslaved, and that makes it even more bizarre that this artifact was seen as a representation and a manifestation of our highest cognitive abilities, so much like them, right? But many people, even in the 1950s, did not buy this comparison between the human and the machine. And one of my favorite critics from the time was a formidable Chinese-American logician by the name of Hao Wang, who proposed that actually logicians had been working with this fiction of man as a persistent and unimaginative beast who can only follow rules, and then that fiction found its incarnation in the machine. He believed that artificial intelligence had gotten it wrong. They believed a false story that human reasoning was somehow itself already algorithmic, and that led them to mistake themselves for the machines once they came on the scene. Wang believed rather differently that actually in people, a particular act of recognition or of reasoning depends on one's genes, on the history of one's mind and body, some essential relation to desire or even race, class, sex, and many other factors. He believed, inspired by his reading of Marx and also Eastern materialism, that there was no universal reasoning faculty, no one set of rules that could account for our cognitive abilities, but that instead, thinking, intelligence, reasoning, these were embodied, they were historical, they were social, they were individual. Wang perceived only vast, incredible differences between the human and the machine. But he thought actually that the power of computing lay in those differences and not in those similarities. He wrote in 1960, and I promise it'll be the end of my long quotes, "The inability to command precisely any great mass of details sets an intrinsic limitation on the kind of thing that is done and the manner by which it is done by people. The superiority of machines in this respect indicates that they might yield surprising new results by making many new turns which man is not accustomed to taking. We are, in fact, faced with a challenge to devise methods of buying originality with plodding, now that we are in possession of slaves which are such persistent plodders. So Wang drew not from the anthropomorphic language of the chess player and the mathematician, but rather of the enslaved person, thought to have had no feelings and and the capacity to endlessly plod. That was the real fiction that was reincarnated in the machine. And in a lot of ways, this is the spirit of computing that is with us today, because as I'm sure all of you know, most of artificial intelligence research today is about what can be done with great masses of details and persistent, unimaginative plodding, most of which is, of course, called machine learning, which takes up not any similarities between us and the machine, but rather the vast differences between them. Machine learning uses computers to do work that we could never do, to make sense of data that we could never traverse or survey ourselves, and often they produce work that we also do not understand. Machine learning is in fact not about knowledge or intelligence or judgment or most of the faculties we might associate with human intelligence and the higher faculties of the human. It is rather about making predictions with lots and lots of data. So many machine learning problems come in the form of what is called classification, where the computer is given a large data set full of examples of something. So for example, we might want to train a system to diagnose diabetes. We'll want to give that computer a data set of examples, each of which is a diagnosis of whether someone has diabetes or doesn't. And in the data set, each of those examples will also have a number of features. Features are just numerical ways of describing the example. So maybe in our diabetes example, each case will have blood sugar level, a number for weight, gender, age, eye color, hair color, numbers that give information about the example. And in our data set, each example is also given a label. In this case, yes, this person has diabetes, or no, this person does not. And the machine will try to learn from surveying all of this data which features correspond with the labels so that it can make predictions on cases whose label are unknown. It wants to assign labels to unknown examples. So the first thing that you have to do is train the data set to make predictions accurately about the known labeled examples in your data set. And once you're confident you've achieved that, then you can try to have the machine make predictions or to classify unknown cases. And one way of doing this, it's maybe the most intuitive, is called the nearest neighbor classifier. And we just ask it to make, when we ask the machine to make prediction for a given set of features, it just finds the most similar set of features in the training data and outputs whatever label that particular example has. Given these features, which label from the data is the closest match, that matches most of the given features on the unknown example? That's one fairly intuitive approach, but beyond nearest neighbor models, you can do all kinds of other machine learning where the goal is to fit some kind of prediction rule to the data so that it makes accurate predictions on that training data. And once you've done that, you can apply it to other models. And under the hood, as probably everyone knows and what we're here to talk about today, machine learning uses what are called neural networks as it trains itself on the data. I made that diagram myself. Neural networks are just complicated rules for mapping features to predictions that you can customize by setting the values of a whole bunch of parameters. And when we train a neural network, we just find values for the parameters and all of the hidden layers that make the predictions look right. And if the predictions don't look right on the training data, you just adjust the parameters. And that's basically the practice. So those are some of the basic ideas behind machine learning, and they sound great, right? Machine learning is being heralded as a solution to problems from poverty to homelessness to the climate crisis. It's the innovation that's going to change your business and disrupt your industry or your practice. But one of the most fundamental lessons from the history of technology is that very often those technologies that are heralded as innovative turn out to be incredibly conservative, in the sense that they reproduce the world around them, reinforce the social order in which they were created, consolidate power and profit with those who already have it. They actually make the world more rigidly the same in some really fundamental ways, even as it looks like they're doing really innovative things on the surface. They embody and materialize the values and the priorities and the ideologies of the people who make them. Machine learning has turned out to be a really perfect example of an innovative technology that is actually quite fundamentally conservative underneath. And there are a few ways in which that is the case. For one thing, machine learning, as we all know, probably really easily reproduces the biases and inequalities in the world around it. Machine learning is trained on whatever data we give it, and that data has been collected from our very storied and problematic history. For example, very simple example, machine learning systems are being introduced to human resources for hiring and retaining and promotions, and those systems are supposed to predict who is going to be good at a given job. But that prediction is going to be based on the features of those who have historically been good at the job, meaning those who have been hired and promoted and retained in doing it. But if those who were historically hired and promoted were men, the machines learning the system may make the mistaken prediction that being male strongly correlates with being good at the job. And machine learning theorists are trying to find ways to mitigate for these kinds of historic biases, but it's hard to get around the fact that our data sets have our history built into them. Another way in which machine learning can be quite conservative is a different observation I hear made less often, that statistical modeling often acts as a self-fulfilling prophecy. The data we collect is meant to describe the world around us. It's meant to take a picture of it. But when we make decisions based on the predictions that come out of that data, we can actually bring forth the very conditions that will make the prediction come true. We can act on them in ways that reinforce bias in the data or reinforce parts of our history that we would actually like to unmake. For example, data-driven prediction is being used across the United States for risk assessment scoring in criminal sentencing. So risk assessment systems assign a number between 1 and 10, say, predicting how likely a given defendant is to show up for their court date if they're released on bail, or how likely they are to reoffend, setting aside the question whether they've offended or not, if they're released as well, or how likely they are to commit a violent crime. But these predictions can in fact create the conditions of their own realization. If a defendant is assigned a high-risk score, then they may not be released on bail. They may receive a longer sentence. They may not be released on parole. As a result of that, one could lose custody of their children, spend more time in prison, spend time in prison before having been convicted of any crime, and these things may cause them to lose their jobs or the possibility of working in the future. And prison time, known to have extremely damaging effects on people psychologically and physically, as well as the other conditions that may be affecting them once they're out, can actually cause them to commit crimes in the future, because we know that some of that desperation correlates as well. So when we make decisions, high-stakes decisions, based on predictions that are trained on our historic data, we risk also reproducing the very conditions that will bring those predictions about. When we punish the prediction of a crime like it was a crime itself, we create the conditions for criminality in the future. So in this sense as well, machine learning is actually quite conservative. It can force its own outcomes onto the world. Machine learning is also conservative in the sense that for all our discussions of the cloud, for all of our experiences of the speed and immateriality of digital tools, big data that supports our powerful machine learning systems continues and relies on very old industrial and colonial practices of resource extraction and the extraction of human labor, as well as energy consumption. The massive data centers, as we heard from Mel Hogan on Wednesday, consume huge amounts of water for cooling, huge amounts of energy for use. All of our data-driven capacities come with that environmental cost. Moreover, many of the computing technologies like smartphones and hard drives that constitute the Internet of Things that produce the big data on which machine learning trains have rare earth minerals like coltan in them and rely also on the extraction of those rare earth minerals, often in unideal labor conditions like the coltan mines in Africa. Machine learning rests on colonial commodity chains and extractive and environmentally destructive practices that we associate with the industrial age and have forgotten somewhat in our digital age. Happily, there's a lot of really excellent scholarship out there now, like that of Ruha Benjamin, Sophia Noble, Virginia Eubanks, journalism like that of the folks at ProPublica, that all explore how machine learning reproduces and entrenches inequalities and biases, even when it claims to overcome them by being objective for being trained on our data, right? And the work of Mel Hogan and Nathan Ensmanger on the environmental impact of our big data practices is also incredibly important. But machine learning doesn't just reproduce our biases or our historic mistakes or risk entrenching them. It does something else as well. It hides them from view. We often cannot look inside and understand the machine learning systems that we are now trusting to inform so much of our knowledge and so many of our decisions and social practices. Those neural networks that I was talking about oftentimes are really deep. In fact, that's the meaning of deep learning, which means they just have tons of those hidden layers, tons of parameters. And all we know is whether or not the prediction rules that come out are accurate for the training data. We oftentimes can't know which parameters or which features are being picked out by the prediction rule as correlating strongly with whatever we're trying to label. For all we know, the machine learning system has found a strong correlation between blue eyes and diabetes, or between eating cold cereal for breakfast and committing criminal acts, and that's how it's making predictions. Of course, it's very unlikely that you would get a good prediction rule out of those sort of spurious connections, but we still can't actually know how any of the given parameters are shaping the rules that come out of systems that are called uninterpretable, which happen to be most of our most powerful machine learning systems. And it could very well be the case that it is making predictions based on school district, whether one is adopted, whether a person has ever had a parent in prison, when it makes predictions about future criminal behavior, thus entrenching the biased assumptions we often make about people who live in communities that are underserved by their state. And this gets to another piece of the machine learning story, which is that predictions are not explanations. Everywhere that we cede knowledge-making and decision-making to machine learning systems, we risk forfeiting our own understanding of why, and with it, sometimes, our ability to make meaningful changes, to reconstruct society to prevent the outcomes that maybe machine learning is able to predict. And some people have found this to be incredibly unsatisfying, if not unacceptable, both epistemologically and also socially. Noam Chomsky, at the 150th anniversary of MIT, the Massachusetts Institute of Technology, was lamenting that you could take a whole bunch of video footage of bees sort of swarming and migrating and use that as a data set to train a prediction rule for when bees are going to migrate. And bee scientists will not care, because bee scientists don't just want to know when or that the bees will migrate. They want to know why they do. We also want to understand better what constitutes the social ills that surround us. We want to know why certain outcomes sort of arise, and machine learning often cannot help us answer why questions. In so many corners of social and scientific and political life, we're collapsing the set of possible questions that we once asked or that we might ask, as well as the agency that would go with the answers, onto simply what predictions can the computer make on the data. Machine learning is applied to bad data sets, biased data sets, real messy data sets, all the data sets, to see what predictions it can make, and this is being heralded as revolutionary. But in fact, we may risk losing a lot. And let's be honest, of course, the most valuable and common and powerful predictions being made are what things we might want to buy, from political ideologies to shoes, creating incredible profit for those who have the right data for that project. But more than that, we are limiting the scope of what we might ask and how we might address social problems and scientific ones when we cede all of our questions to these data-driven predictions as though that was the most powerful kind of knowledge there is. So I started by talking about the historical fact that we were once the measure of the machine, that early artificial intelligence was an attempt to reproduce human intelligence, to build our likeness, our knowledge, our reasoning into the machine. Needless to say, in spite of a somewhat tenuous comparison between neural nets and our own neural synapses, we are no longer the model on which artificial intelligence is based. Machine learning practitioners, for the most part, want to be able to solve problems in hard problem domains and are uninterested in whether they teach us anything about ourselves in the process. But if we forfeit our agency and our understanding and our decision-making and our science, our scientific questions, to power systems and methods that we can't open up, and if we collapse everything onto prediction, we will have been displaced in another way as well. Our own knowledge, our agency, our ability to remake the world we live in gets harder and harder the more we build older versions of it into the machines. And of course, I'm not advocating for a return to traditional artificial intelligence based on the assumption that we are mere machines that can be replicated in the metallic ones. But I do think that we must once again be the measure of the machine. Or maybe, as I think Tega will suggest and has explored in her amazing art, that perhaps nature or the environment might be a new measure of the machine. The machine needs to be held accountable to systems of values that are not necessarily translatable into the constraints or conditions for a prediction rule. We need guiding principles beyond how accurate are the predictions on the training data. It is not enough to try and find a constraint for a prediction rule that captures one mathematical definition of equality and think that you've solved the problem. Instead of asking, what can we get computers to do, we must also always ask in tandem, who do we become? What future possibilities for ourselves do we close down? What will the world look like? What parts of our past do we want to get rid of rather than reproduce? How do we do that? We may need to make real changes to make a world that produces really different data if we want to train machine learning systems to be powerful on it. So I think the punchline maybe is something like, we are in fact so different from these machines, and I think should lean a lot harder into that and embrace it a little bit more. So I'll stop there.
Stephanie, that was a fantastic introduction to all the problems we will try to discuss in basically an hour. A crash test into the logical and political fallacies of machine learning. Now I understand it's good to read a biography in between talks so we can breathe a bit, while in preparation to the next talk by Katharine Jarmul. The idea of today was indeed to start with Stephanie depicting, making an overview that actually was very precise, analytical, the historical, the gradual construction of the system and all the problems we have today with them. And with Katharine Jarmul to have another approach. Katharine is invited indeed to show how the vulnerabilities, the technical vulnerabilities, and as a sort of also introduction of a new art of hacking that has to deal with this complex system. Katharine Jarmul is head of product at Dropout Labs, a company enabling privacy-preserving machine learning and an internationally recognized data scientist and coder. She worked for large companies in the US and Germany implementing machine learning systems with a focus on privacy and security. Katharine is an author for O'Reilly and frequent keynote speaker at International AI Conference, and I think that we should include also the Chaos Computer Conference among this International AI Conference, right? Okay, please welcome with me Katharine on stage.
All right. I will wait for my slides, and if it's okay, I like to walk around sometimes, so I'm going to try to grab one of these. Is that okay? Is this thing on? Whoa, magic. Okay, I'll wait for my slides, but first I just want to say I'm very, very excited to be here. I always wanted to be an artist, but let's just say the talents were not there. So it's always really inspiring for me when I can go be around like some of my fellow speakers and have all this inspirational art and messaging. I think it's this one. Super. Yeah.
This one.
Thank you. And so, but today what I'm going to dive into is what I'm actually good at, which is not really much things creative, but instead things around math and computers. And I'd like to say that I try to use them for good, which means although I have been paid in my life to build AI, I also have a deep passion for hacking AI. And today we're going to learn a little bit about how to do that, and we're going to talk about why we might want to hack AI systems. Now, I use the term AI almost always in quotation marks because, as Professor Dick very well pointed out, perhaps there is nothing intelligent in the artificial intelligence. And perhaps that is something that we should all question on a regular basis when we hear terms like AI. And so when we think of, so first of all, who here was in the workshop for adversarial examples? Did anybody here attend the adversarial workshop? Okay. For the few folks with their hands up, round of applause. And please go find them, make friends with them. I am happy to also be a mentor here in Berlin. We need more people learning and focusing on hacking AI systems. In the field of AI or machine learning, we often talk about the hacking that we think about today as adversarial examples. And I'll dive into those in a minute. A lot of times they attack computer vision systems like this adversarial turtle. But adversarial attacks on machine learning systems are actually quite old when we think about computer science history. These were first starting to be developed around the time that people started using machine learning in production systems, which would have been about 20 years ago. So by no means is the recent hype around adversarial examples as part of a much longer history of learning how these systems can be tricked or fooled, most likely or often by adversaries in a security sense, like people trying to get around a spam filter or something like this. Now, the adversarial examples that everybody's having a lot of fun with and making art with, and I think Fabian will be sharing some of his work later around this, are something more akin to what we're talking about here, which is essentially attacking deep learning computer vision models and making them essentially see something or misclassify what is being shown to them. And so from every angle, this 3D printed turtle that we all can recognize as a turtle, perhaps as a slightly psychedelic turtle, it has, when you can see it better, it has fun patterns on it. And this adversarial turtle, by one of the most common and prominent computer vision models, is being classified as a rifle. So, don't put it in your pocket when you're going to the airport. No. Thankfully, we have humans checking that, not AI yet, at least. Anyways, so the fact is that it may seem that we can add random perturbations, but actually, there's an entire science now around how we can carefully perturb or add noise to these inputs and therefore make the model misclassify, make it make a mistake. Mathematically, we could say that we're raising the potential for an error. We're raising the potential for uncertainty. And that is essentially what we do when we learn how to create adversarial examples. And so how does it work from, let's just get an intuitive sense of how it's working. This here is a visual example of a common way that we train neural networks or deep learning networks that is called gradient descent. And essentially the idea is when we train machine learning, we're just showing it a bunch of examples and we're telling it whether it was right or wrong. And when it's wrong, it takes a measurement of how it's wrong, and it essentially tries to learn from that. right? It performs a series of equations, usually to update and then start again. And so when we start, we're probably in one of these high red zones, which is high error rate. And then as we go through the training process, and sometimes we go through millions and millions of examples, now sometimes billions of examples, we eventually hopefully end up at a low error rate, which is perhaps down there in the lowest corner, or maybe is another, what we would call local minimum. And so when we create adversarial examples, what we try to do is we try to push back up the hill. And so we want to push the perturbations so that we're going essentially back up the hill or in a particular direction towards a different class. So when we take the turtle and we say we want to become a rifle, we have to walk towards the rifle space if we want to think of it as a multi-dimensional space. Now, of course, this is a slight simplification because normally instead of three-dimensional space, we're dealing with thousands, if not millions, of features. And for this reason, it is very difficult for us as humans to reason about that in a meaningful way spatially. However, we're essentially doing that targeted push towards a different part or different space of the model. Now, this doesn't need to only be used for, let's say, misclassification purposes. In fact, people have taken this idea and applied it to a lot of different concepts. More on that later, I believe, from some of my co-presenters. But one of the interesting concepts when we start thinking of hacking AI systems, or maybe using AI systems to hack other humans, is we think about steganography. So steganography is the ability to hide a message in another message. So you and I just see an innocuous message. However, if we had the key, let's say, to unlock, or the method to unlock what the true message was, then we would get a secret message. In a paper called Deep Neural Networks Are Easily Fooled, the authors kind of decided to take a look at this application. And what they tried to do is they combined what we call an evolutionary network, which is one that's probably better at walking around and exploring. I will not compare it to human creativity, very different, but it will go look in different places for something that might solve the problem. And they combined it with a pattern-based and a color-based system. They merged those together, and they were able to create the images that we see here. Now, that's essentially, I guess, one could call it art. I don't know. Is it art if a machine makes it? I don't know. It's a good question. I think one that was explored throughout the conference. But what we can take a look at is that all of the computer vision, the very popular computer vision model that they used, will see these as the text underneath each of those images. Now, I know probably it's hard to read, so let's take one, the top right one, the green with kind of the circle. Now, it sees that as a rotary dial telephone with like 99% accuracy. And the bottom left one here with the circle, that is a projector with 99% accuracy. And there's many things in between. So things that, yes, perhaps we can see some similarities, but that are actually highly confident from this computer vision model that they are what they are. Now, by no means do I think that this is a secure way for us to send secret messages to one another, but I propose it as a concept of how we can use this idea of adversarial images and adversarial examples to explore new ways to use them for our benefit. Which brings me to adversarial fashion and design. Now, how many people have seen at least one of these images before or are familiar with the concept? Okay, super. So we'll start on the left here. This is some work done by CV Dazzle. And CV Dazzle attempts to open source different designs that one could use for makeup and facial art and design to evade facial recognition models, such that when you're walking by on a camera, it will no longer recognize your face as a human face. Here we see a very nice rendering. Again, all of the patterns are open source. You can download them. You can experiment with them yourself. And they target a model, they're an attack essentially on a model called OpenCV. That's why it's called CV Dazzle. And OpenCV actually is not very intelligent. Most of these systems are not very intelligent. And it's not even a deep learning system. What it tries to do is it tries to identify facial markers. So it will identify the corners of your eyes. It will identify where your chin is, where your forehead is, these types of measurements. And then it will try to determine who you are, first off, if you're a face, and then second off, who you are based on the different distances between the facial markers on your face. Because you are a valuable, unique snowflake, and your face is therefore also very unique. And so what CV Dazzle says is, well, screw your facial markers. I'm going to create my own. And how we do that is we're able to add different, essentially adversarial input by changing where our jawline is, as we see here, by changing where our mouth is, by changing where our forehead is. And you could do this simple, this low tech, so to speak. If you weren't feeling very glittery that day, you could do it simply with face paint or anything else. And I behoove us to find a way as a society to be totally fine with wearing that to work. So, if we can be totally fine with everybody showing up looking that fabulous to work every day, then we have won the facial recognition game. On the right-hand side, we have a slightly different type of response to surveillance systems and machine learning in surveillance systems. We have a company called Adversarial Fashion, and what they do is they make these license plate-styled different pieces of clothing. And I'm sure everybody's heard of Smart City. They're trying to make Berlin a much more smart city. I hope that doesn't happen. But the idea is that we put cameras everywhere, we put sensors everywhere, and then somehow something better comes out of our lives. Yeah, I don't know either. Very confusing. And so what we have here on the right is we have somebody who, when they're walking by the smart city, they're like 20 cars at once, which is pretty fantastic. And it's essentially a way of sending spam mail back to sender, you know? You say, no thank you, here's 20 license plates that don't exist. They also have ones in European, but rather than buy, we could probably make, you know, just saying. And the goal of that is, again, most likely you're not going to actually evade surveillance, right? Because you're still recognized as a human and all these other things. So from a security perspective, I don't want you to walk around like this and think that they don't know who you are or where you're going. But what I do want to point out is that we can send a message back to the system. We can send a message back to the watchers. And we can send it junk mail back to the watchers, which is important. Because a long-running attack on machine learning systems is actually called a poisoning attack. And the way that a poisoning attack works is we send the machine a bunch of junk data. Now, okay, we could possibly send it junk mail, but we could also send it very specific junk mail so that it really messes up. So, in this particular, I guess that would be like a phishing attack, right? Like, anyways. Okay, so in this particular attack, Professor Battista Biggio, that has a group that works on attacking machine learning systems in Italy. He is very, very prominent in this field and has done a lot of amazing research on poisoning attacks and other adversarial attacks. And we can see that the face model starts over here. So you can think of this face model as being built for you personally. Is there to unlock, what's it, face pay or all of these new systems where just show your face and you can buy things, or show your face and you can unlock things. So it's essentially targeting a system like that. Now, for most of these systems, your face changes over time, and so they have the ability to say, I'd like to update my image. And so the group used that update your image ability to send slightly modified, but strategically modified, again using math and using a special attack vector, to change the image. And ended over on the right, where the person looks much more like they're wearing glasses and looks much more, their facial structure has changed a little bit. It looks much more like they have a different chin, and so on and so forth. And so this is, again, an example of this targeted attack where we want to make it look like a different person. We can do so by giving special, noisy updates, right? And so that is one way we can poison systems. And I really like the idea of poisoning AI systems because they're not human, right? So like you're not killing anyone. You're just poisoning a machine. And the machine is not treating you very nicely, so I think it's totally okay. From an ethical perspective, I think we're okay. Should poison more computers. Anyways. And so one way, if you want to try out poisoning some computers with me, let's do it together. One of the ways that we can do that is maybe you can download and install Privacy Possum. Now, Privacy Possum, it is a Firefox extension. It is built by the Mozilla Foundation, and one of the core contributors open sourced it, so it's also, if you know how to use GitHub or you know somebody who knows how to use GitHub, you can download it and install it yourself. So it's all open source. And what Privacy Possum does is it kind of takes a different angle to online tracking. Because unfortunately, the way that online tracking happens today, especially let's say from like a large-scale machine learning perspective, it is quite difficult to remove yourself from that system. All the ad blockers you can install, all the tracking blockers you can install. This helps, yeah, and you should do that, but it's by no means 100%. Because there's unfortunately a lot of other things that people can track about you, like your IP address or your browser, all of these other things. And so what Privacy Possum tries to do is it actually just inserts noise. And so it will send back arbitrary URLs. And it will change and remove URLs. And for the trackers, then, it will be sending, essentially, like these junk messages, this noise, this spurious data, back to whatever the tracker is. And the goal, therefore, is not to completely avoid being tracked, because unfortunately, that is extremely difficult to do, but instead to make your data worthless. The more we can make all of our personal data worthless, the less money can be made off of us and our data. And I think that this is one way that we can collectively say that we do not want to be a part of this system where our data becomes another person's money. And so, Privacy Possum is pretty cool. Other projects like that exist as well, and I'm always excited to hear about new ones. So if you have one, let me know. But that same idea of poisoning your data is by no means, let's say, a revolutionary new idea, especially here in Germany. A few years ago, a friend of mine who was involved in the CCC for a decade before, she let me know and said, yeah, didn't you hear about the privacy card? Like, obviously, we've been doing this forever. And I was like, no, I don't. Tell me about this. And so I heard about the privacy card for the first time. Now, the privacy card was back in the early 2000s, and this was around the time that the payback program started. And just in case you're not based in Germany, the payback program is like this little rewards card for shopping rewards, and you get points and you get discounts when you use it. And essentially, it's a great way to incentivize people to give up their entire shopping data for like 5% off or 5 cents off, and so on and so forth. And so members of the CCC, along with a local hacker organization, got together and they figured out a way to make new cards, but all with the same number. So there was like lots of cards with all the same payback number, which is great. Because then the word got around that you could just mail to this address, you could just mail five euros, and they said they would also do it if you have a handwritten letter for free, but if you could afford it, 5 euros, and then you get back this privacy card. It even looked like this, and then the back had the little scanner, so you can just swipe it. And so everybody was using these, supposedly, and of course, Reve eventually got word of this, or the folks that are running the payback card, and they eventually shut it down. But it was this mass action where the data all of a sudden would look quite insane. Somebody would probably be buying wine and tampons in Berlin, and somebody else would be buying beer in Düsseldorf, and a third person would be buying hot dogs in Munich or something. I don't know. I don't know what they eat down there. But yeah, so this is all a thing that you could do and be a part of, and the account ended up with more than 20,000 points, and they had to take it to court to shut it down, and it was a whole thing. But for about 2.5 years, this worked. And this was a way that you could get the discounts and the rewards, and they cannot get any useful data from it. And so my challenge to us today, a question that I want us to ask ourselves, to ask each other, to ask our loved ones, is can we collectively topple surveillance capitalism? That would be my life goal. Then I could die happy. So please, please, I don't have much time left. But no. We can do this. This surveillance capitalism, they let it become fully automated. So now we can attack the computers, remember, with no empathy for computers because they are not people. So what if we, every time we saw a free service, the free Wi-Fi, and they're like, just hand over your email, it'll be fine. Nothing is free, right? So they're selling your data. What if we all use the same email address? My favorite one, I use one, a bad word in German, it ends in loch, @yahoo.de. So if you want to join me, let's do it. Yeah, let's do it. And then they can't sell that because they're like, wow, this is all around the place. Anyways, what if we, whenever we're asked for a mailing address, but we're not actually getting anything mailed to us, what if we all use the same postal address? Now, we could ask the nice folks here at Volksbühne, or maybe we should just send it to the Reichstagsgebäude. Yeah? I'm with it. I'm on board, okay? And what if we all decided for one day to wear the same thing? To wear a wig and the same coat all around the world, as far as we could reach, in every smart city that is surveilled. What if we did that too? So I would suggest, this is a coat. It protects against the Bluetooth tracking and all that other stuff too. It's made in the Netherlands. And then I have a really nice red bob wig. So next Friday? Anyone? Okay, I hope so. So I know it's crazy and it's silly and it's funny, and I really appreciate that too, because I think we should be crazy and silly and funny in the ways that we revolt against these systems. I also get a lot of inspiration from the Fridays for the Future and the climate change movements that are happening all over the place to take it to the next level. Because as I have seen as a member of this industry, the industry is not going to change itself. I speak at lots of AI conferences, and they always say, you're very edgy. So they're not going to change themselves, and I can yell all I want, but it's only a few voices, and it's not really going to fix it all. But if we, as a collective group of humans who deserve to be treated as humans, who do not deserve to be classified by algorithms and machines that are not even intelligent, if we collectively revolt against these systems, if we poison them, if we attack them, together as humans, then I believe we can hopefully inspire the change that I'm hoping to see in my lifetime here. Thank you very much.
I'm happy now to continue. There is a phone here. Maybe it belongs to somebody's smartphone. It's okay, I will stop it. We continue now with two respondents. The first one is Fabian Offert. Fabian is an AI scholar working on the epistemology and aesthetics of neural networks. He's a PhD candidate at the University of California, Santa Barbara, and a research associate at the Friedrich Alexander University Erlangen, Nuremberg. Sounds like an aristocratic title. And in the FG cluster, the digital image. And I'm also very happy that Fabian has joined also as a collaborator. Our research group came at the Hochschule für Gestaltung Karlsruhe. One of his last texts is about the past, present, and future of AI art in the Gradient Journal, but I invite you also to check his website because there are like very recent and timely analysis of the constitution and composition of neural networks today. So please, let's welcome together Fabian on stage.
Thank you, Matteo. Can you... Keynote. It's that one.
Yes. Okay.
Okay, great. So first of all, thank you both, Stephanie and Katharine, for this amazing look into the historical and technical deficiencies of statistical models in general and neural networks in particular. So in my work, among other things, I look at how neural networks are used in the sciences. So I'd like to respond to both of your talks by showing a few brief examples where these deficiencies that you mentioned that we've seen become not only politically but epistemologically challenging because they affect the way that people do science and they affect the way that science usually works. So the very simple hypothesis that I would like to argue for here is, and given that, as Stephanie showed, predictions are not explanations in the sciences, I would say neural networks significantly blur discovery and invention. And when I say neural networks here in this specific case that I'm going to talk about, or these cases, I'm mainly referring to a specific architecture of neural nets called generative adversarial neural networks. So it's a mouthful, so I'm going to say GAN for the rest of the talk. So these are networks that can learn from a data set to produce images that look like they came from this original data set, right? They learn to imitate, not replicate, but imitate the essential features of the images in an image data set. So the most prominent example is probably a GAN that can create realistic faces. So this is from a neat little website called thispersondoesnotexist.com, and indeed, thispersondoesnotexist.com. So it's an imaginary person that you see here that has been generated by a GAN. GANs have also been used extensively in the arts. So here, for instance, you can see a GAN that I trained on 50,000 images from the Museum of Modern Art collection. And the aesthetic question here, if we watch these images appear and disappear, is, of course, can a neural network produce anything new and interesting in the aesthetic domain? Can it facilitate aesthetic discovery? So if we look at the MoMA GAN, the question becomes, does this produce only MoMA-like images or actually MoMA-worthy images? So I'll leave this question unanswered for now, or I'll leave it to you, because the important thing I want to point out is that this question can be directly translated to the scientific context. So we can also ask, can GANs facilitate scientific discovery? So it turns out that GANs can be extremely useful in cases where scientists lack information about an object of discovery or an object that they're interested in. And one example is super resolution. So I will leave you to the X-Files here to show you what super resolution means. And there are so many other examples out there that this has always, almost become a meme at this point. So of course they want to see the details of what happened here, right? And you're laughing, of course, because we all know, and this is the essence of super resolution, finite resolution images can only reproduce finite detail, right? But it turns out with GANs, there's a way to go beyond this limit, which is called the deconvolution limit. When we use a GAN, it has learned something about the class of images from which we are trying to reconstruct a sample. And that way, what we can do, for instance, is we can reconstruct pixelated faces on the top here. But here the problems start with GANs and the sciences. So the reconstructed faces that you see in the middle row, in the middle column here, are of course different from the originals, because as you can tell, there's almost no way to reconstruct something from an 8x8 pixel image like those on the left. So they're different, but how different? So is an image of a person that looks almost but not quite like a person still an image of this specific person? Are we hallucinating new persons instead of reconstructing lost originals? So have we crossed the boundary of discovery and invention? So instead of discovering things, are we actually inventing things? And these sound like speculative philosophical questions at best, but I think they gain some epistemological significance when we look at real scientific methods that use these exact approaches. So this is from a recent paper that uses GANs to denoise images of galaxies. And the problem is, though, that by using a GAN, the potential knowledge that these images contain here becomes identical with the knowledge that the GAN has already learned, right? The space of discovery is absolutely identical with the space of knowledge that the GAN already has. So if there was anything unknown to be discovered about the celestial objects in these images, it would be overwritten by the reconstruction. And of course, you might say that any optical medium, and I'm sure you know that, influences the space of discovery that it facilitates. So this is what optical media do. So using a telescope opens up a different space of discovery than observing the sky with the naked eye, of course. And even when Galileo invented the telescope, he was immediately skeptical, right, that it would distort the truth somehow. And by the way, the famous black hole image that you see on the right is facilitated by computation in every conceivable way. But with GANs, the space of discovery suddenly is not constrained anymore, but it is completely replaced. So while we think we are seeing through a GAN, we look at something with the help of a GAN, we're actually seeing into a GAN. So GAN vision, this is kind of my point, is not augmented reality, it's almost virtual reality. And recent experiments in the sciences have shown that this has severe consequences across many, many domains. So here's an example from medicine, where they used a GAN to successfully translate between two different types of images, so between MRI and CT images. You can imagine that this is a kind of like important thing to do in medicine. But it turns out that if you use training sets to build this model that are only slightly unbalanced, so for instance, one of your data sets that you want to translate from contains more images of cancerous tissue than the other one, the GAN will start to hallucinate tumors because cancerous tissue is the only thing that it knows, right? So when the data set is unbalanced, suddenly the GAN will start to hallucinate features that are not there or should not be there because this is a simple image translation. So the conclusion is, I think GANs do blur discovery and invention, and I think this is another problem on top of the whole stack of problems that we've seen in the talks before that we have to tackle in this new reality of artificial intelligence. Thank you.
Thanks, Fabian. That was illuminating into another dimension of this complex space. I'm happy now to welcome on stage Tega, that is already known here at the festival because of their contribution to the exhibition. Tega is an artist examining ecology, environmental engineering, and the use of data systems. Tega is an assistant professor of integrated digital media at New York University, and she works with the Processing Foundation on the Learning to Teach conference series after already contributing to the exhibition here of Transmediale and many other projects. Please, Tega. I'm very bad with formalities. I would like to invite our speaker maybe to the armchairs here, and we follow your talk all together. And we redistribute smartphones as being lost in the process.
Okay, I have a couple of slides too. I will attempt to bring up quickly. Okay. So I just will start by just briefly describing the work that is in the exhibition here that maybe you've had a chance to see. The piece Asunder, it's a collaborative work, as Matteo's introduced already, and it really responds to a growing interest in the application of AI to critical environmental challenges by situating this as like a literal proposition. So you see this fictional environmental manager that proposes and simulates future alterations to specific sites around the world. The work combines machine learning image-making techniques with traditional climate modelling techniques. So on the right here, you see a GAN-generated image that is modifying an area in the Netherlands. On the left, you see the historic images of that particular region. Once our system has generated this hypothetical scenario, we then use a climate model, an Earth and climate model called the Community Environmental Simulation Model, to simulate what that scenario would look like and what would happen into the future. So at play in the piece are these two different approaches to modelling. One is a statistical modelling process that Stephanie talked about. That's this uninterpretable process based on correlation, alongside a conventional Earth model that is built from theory and built from equations. We can understand the parameters in this particular climate model. There's many of them. These are some of them taken out of the atmospheric component of the model. But all of this can be traced back to papers and theories and observations coming out of the earth sciences. So we see these two sort of different approaches next to each other. So just quickly, with the stunning hype around machine learning and the very existential environmental challenges we're facing, we're seeing a lot of this, right? A lot of like, AI is going to save us, we're going to have robots that are going to deal with like species problems and, you know, virtual fences to manage how different animals can move around, predictions, you know, there's a whole lot of examples up there. And so I just wanted to talk quickly about, you know, I think some of the limitations we really need to focus on when it comes to applying machine learning in an environmental context, and, you know, they're numerous. I guess it's a very evocative idea, you know, the Anthropocene and climate change means that wilderness is no longer about an absence of humans, but it's about, you know, autonomous ecological processes. So wilderness is about ecosystems being able to like autonomously continue to exist and to thrive. So it's very tempting to throw one at the other, right, and think that we can use autonomous technologies to then, you know, maintain or produce or manage environments in a way that is beneficial. And a lot of my work is kind of looking at these questions of like the basis, the assumptions we make when we build systems and infrastructures that manage environments. And can we sort of rethink them? Can we imagine and build systems that create space for like multi-species relationships, or that create space for other agendas more than just the human? And I call this type of work eccentric engineering, so an attempt to sort of de-center the human in engineering. So just to, I guess, wrap this up, I mean, I think to bring together the sort of presentation from Stephanie with the focus on adversarial hacking, you know, adversarial hacking, I think, is a very spectacular demonstration of the fallibility of machine learning systems, right? So this is one of the problems with them, that, you know, they can be hacked, that they can indeed fail. And I feel like the adversarial hack is a really effective way to sort of demonstrate this without having to have, you know, a deep understanding of the literature. So I think as an activist tactic, that is very useful. To return to this question of like, what are the limitations of applying machine learning in an environmental management context or environmental inquiry? So there's a few else that I see apart from this fallibility issue. One is that, you know, we simply don't have that much data. You know, we only have around 200 years of weather data in a lot of places. You know, recent studies around biodiversity estimates that we don't even, the majority of species on Earth are unknown to science, right? So there's this real limitation to what we know in the context of environment. The next is that environments change in really unexpected, unprecedented, and non-linear ways. So the way that machine learning systems are conservative, is the assumption that the past is representative of the future. Climate change very clearly demonstrates that this is not the case. We are like off the map with where our Earth system is headed. So using a system that is making this assumption is obviously, we need to be very critical of that. I think we often see this idea that decisions are going to be depoliticized. You can see that up there. Machine learning is not biased by the human mind is mentioned in one of those articles. And, of course, I think this totally overlooks the fact that a lot of the environmental challenges we face are coming out of histories of violence, colonialism, patriarchy, right? So the idea that, these systems built by a very homogenous group of affluent people, largely based in the US, that's going to address these problems of environmental justice, I think, again, is a problem. A couple more, just also fodder for conversation, is the assumption that the environment is a rule-based system, I think, is as equally problematic as the assumption that the human brain is a rule-based system. And Anna Singh's work on mushrooms, and she talks a lot about the indeterminacy of relationships and the relationships we have between species and within ecosystems, comes to mind here of why we cannot just assume that this is the case. And the other thing that really does keep me up at night that I'm very concerned about is that, the focus on prediction, the focus on machine learning, the focus on these technologies in the context of environmental problems distracts us from the fact that they are largely social and political issues now. They're born of a situation that is not about a lack of information, it's not about a lack of our predictive ability. And so it's very easy just to throw tons of resources at all this cool stuff and forget that I don't think that this is going to address, the issues that we are facing and that are concerning me in my work. So I'll leave it there and maybe we can pick up on some of that. Thank you.
It's now basically impossible to make a summary of this complex problem we are entering. Compared to the network culture of the 90s and the debate of network theory of the 90s, something else is building up here. So I would like maybe to ask, with brainstorming 5 minutes, super fast, what is the difference compared to the past? We are clearly living in a moment of a pure mythology, mythologization of great techniques. If we were using data analytics rather than the term intelligence, things would be much clearer and marketing less effective. For me, it would be interesting to understand, what is the difference compared to the vulnerabilities we were trying to tackle in the 90s, for instance. The internet was developed as a form of architecture that would survive an attack from the outside, but data center, paradoxically, the infrastructure data center centralize again some kind of the power architecture of the net. And on top of that, data analytics, artificial intelligence are a form of monopolies that have different point of attack vulnerabilities. I would like maybe just to brainstorm this to see, what could be also the forms of activism, counter politics towards this, infrastructure of knowledge. Stephanie, do you have any idea about this?
About differences between the moment we're in and the moments we've been in the past?
What's to be done today?
What's to be done? I think Tega just, alluded to the only thing that is to be done, which is that, social and political problems can only be solved by social and political means. They are never solved by technologies. Liberal Democrats in the United States in the 1990s believed that the internet, if just everybody had a PC and a modem in their house, that was going to solve all their problems about unequal education access. It's going to solve their unemployment problems. It was going to rectify the poverty of the rural South. And of course, none of those things happened, but it's absurd that anybody expected that they would. Every time we seek to solve a technological or a social problem with a technological solution, I think we risk forgetting all of the social and political tools that can be at our disposal. Vote, run for office.
you want to add something?
Yeah, it was obviously that point, most important point. A secondary point that I was a little bit inspired, Matteo, by what you were saying is the concept. There was this concept of the internet as the great equalizer, right? And there's still that idea is like, if we could only get everybody connected to the internet, then everybody would have access. Now, of course, there's some good things, right, about having internet access, and there's some ways that that can be decentralized in meaningful ways. However, the way that most of the internet works today is we buy internet access from a conglomerate that is then able to track our every single move on the internet and is then selling that in a anonymized fashion, wink, wink, nudge, nudge, to other companies to target us via advertising. As somebody that works in privacy-preserving machine learning technologies, it does not have to work that way. We can build decentralized networks that are separate. We have techniques where a group of us can get together, train our own model, and see the benefits of our own data without ever connecting it to the internet. So I would say, let's reclaim the idea of networks in a more decentralized way and figure out ways to make that knowledge and technology available, especially to communities at risk.
Yeah, my question would be what is the scale of confrontation in the specificity of AI monopolies, and if machine learning indeed is a form of accumulation of knowledge, know-how, that actually change many of the rules of the game. Fabian, do you have any comment about this different magnitude that we are facing within the mathematical construct of machine learning?
Well, I mean, I would say that if you look at these systems analytically that we have today versus the so-called good old-fashioned AI of the 1990s, for instance, I think the underlying philosophical assumptions are still the same, pretty much. So that's maybe an attack vector that you want to consider. I mean, Philip Eger says AI is philosophy underneath, right? And I think that's still true, and it's a specific philosophy, which is essentially Cartesianism. So like the hope that something magnificent will emerge if only we throw enough data and computation and power and things at the problem. And this has not changed at all. So if we're talking about attacking like the underlying structure, then this is something we should consider, I would say.
At this point, we have, according to the schedule, only 2 minutes left, but maybe we collect a few questions from the audience because I don't know if that was part of the plan, but if somebody else wants to just... Okay, I'm sorry for that, but in case, but we have only 2 minutes left in case you make questions here in Berlin and we answer somewhere else, like in Karlsruhe, as we usually do.
I think we should call it machine plodding from here on
Machine?
in. Plodding. I think that was a beautiful term that I would like to see in circulation. Art exhibitions about plodding, maybe that would help us sort of put it in a better context. I mean, a thing I think about a lot is your question about scale, and I think a central issue here is that like a lot of the artistic works we're doing, a lot of the scientific work we're doing with these technologies is relying on companies like Google, data sets that have been scraped from God knows where, the internet, our shared resources. So like they're privatized, right? A lot of these technologies are existing in corporate context. And so therefore the problems or the questions that can be asked or the questions that they can address also are confined to that context. Like I want to see like, image recognition and machine learning systems to automatically like send violations and fines to like people who are polluting waterways, right? But corporate America is not developing machine learning for those sorts of problems because of the ownership of these technologies and the way that they rely on that system.
Yeah, we have only very few minutes left. I don't know, there's a big responsibility to me to wrap up and introduce. But I don't know, maybe we take one question, just one, just to show that we are slightly democratic in our attitude. Vani, yes.
Very quick one. I would be a little bit cautious about saying that technology is not a solution and the solution will come from politics. from society, because politics and society are technological as well. Voting is some sort of old technology, and the laws and how they are made, different type of technology. Probably technology is not completely out of the equation. Probably we should rephrase the word technology.
Sure, yeah, of course. I mean, I come from a discipline that has insisted for decades that technology and society are co-produced, that we build technologies, they shape us back, you can't disentangle them. But that's not the same thing as assigning or attributing all of the agency to technological solutions unthoughtfully the way that so many people do. One of the things I've actually been the most excited about in terms of critiques of AI are actually the work of people like Meredith Whittaker, who are helping sort of laborers who work for technical companies organize, unionize, push back against the way their research is being applied. And that looks like a social mechanism that can take a technical form. So we have to change both at the same time, and we will not change the social and political structures that have brought us here without doing social and political work. There isn't going to be an app, you know, to save us from surveillance capitalism, right?
Okay, thanks, Steph. I would like, to continue the conversation maybe with just the proposal to gather after this event and continue maybe after the bar. Please maybe pick up a copy of this map that Vlad and me have been brainstorming as indeed an attempt to map all the friction and conflict between the social form and the technical form. And with this kind of workshop idea at the end of this event panel, I would like to thank you all for this contribution and for your presence here tonight at Volksbühne. And keep on talking about complex things.